members felt very excited, and when Arnav and Shiva requested me to give this talk, I happily agreed. There is also another reason why I agreed, and that will become clear as I proceed. So let me begin now my talk. So first of all, let me point out that as far as the frontiers of physics is concerned, many other people also look at it this way, that there are frontiers at very large scale, and cosmology is one such example, where one studies the large scale structure and evolution of the universe. Astrophysics is another example, where one studies physics of astronomical objects like black holes, neutron star, etc. Then there is, of course, very small. I'm sorry, let me try to move my screen a little bit if I can. No, it's possible. Okay, so very small is the domain where one studies elementary particles. So one studies essentially the fundamental constituents of matter. And related to that, of course, there is a question of interparticle interactions, namely what are the fundamental forces of nature. Now, it's also known that very small and very large are actually related. But this year's Nobel Prize has been given in an area which I would call is the domain of very many. And here one studies noise, nonlinearity, and non-equilibrium systems, particularly structures which are often self-organized with their respective emergent properties, and also the processes. These processes are often either random or chaotic or both. And this is the area of complex systems. Now, one may immediately ask, what is the definition of complex systems? What are the characteristics and all that? And these are the things that I will discuss towards the end of this lecture. So first, let me go through the press release of Royal Swedish Academy of Sciences. For the Nobel Prize in Physics 2021, the announcement says, the Royal Swedish Academy of Sciences has decided to award the Nobel Prize in Physics 2021 for groundbreaking contributions to our understanding of complex physical systems, with one half jointly to Manabe of Princeton University and Hasselmann of Max Planck Institute in Germany for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. And the other half to Giorgio Parisi of University of Rome, Italy, for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. Now, I'll draw your attention to some key words. These key words are complex physical systems, then disorder and fluctuations. And in this lecture today, I'm going to explain these words, and in the process, I'll explain Parisi's contributions. So in this talk, I'll discuss only Parisi's contributions, and that too from a historical perspective. Towards the end, I will point out the conceptual link between Parisi's contribution and those of the winners of the other half of the Nobel Prize. Now, before I begin the actual contributions, it may be helpful to go through Parisi has received many awards and recognitions. So let me just read out the citation of the Boltzmann medal that he got in 1992. So he received this medal for his outstanding contributions to statistical physics, and particularly to the theories of phase transitions and of disorder systems. Parisi's deepest contributions concerns the solution of the Sherrington-Kirkpatrick mean field model for spin glasses. This achievement forms one of the most important breakthroughs in the history of disorder systems. And I have intentionally put them in red color. This discovery opened the doors to vast areas of application, as for example, in optimization problems and in neural network theories. Another award that he got was Lars Onsager Prize of American Physical Society. He got it in 2016. And that is for groundbreaking work applying the spin glass ideas to ensembles of computational problems, etc., etc. So what you find is a common between these two is this, concept of spin glasses. So first question is, what is a spin glass? Why are they interesting from the perspective of physicists? What was Parisi's contribution in understanding physics of spin glass? More specifically, what is the mathematical origin of the concept of replica symmetry breaking that he introduced, and what are its physical implications, and what does it have to do with complexity? So I'm going to try to answer these questions. Now, this lecture is a tribute to Professor Phil Anderson, who passed away last year, and for two reasons. One is, of course, he was pioneer in the research on spin glasses, and another is that I'm deeply indebted to him because he supported and appreciated my work, and because of his recommendation, my book was published by Princeton University Press when I was just a postdoc. So this lecture is a tribute to Professor Anderson. So spin glasses, the word spin appears there. So for those who are not familiar with the concept of spin, let me introduce it. So I'm introducing non-interacting classical Ising spins in a magnetic field. So what are these? A classical Ising spin can take two possible values, s equal to +1 and -1. And normally they are schematically shown as arrows, up arrow and down arrow. There is no arrow there. It is just a way of depicting, pictorially or graphically the states. So states can be +1 or -1. And the spin can be in an external magnetic field, which is shown here. So the energy of the spin in the magnetic field H is given by this expression. So what is mu? Mu is the magnetic moment of each atom. And for convenience, most of the time, I will take mu equal to 1. So now, if this is the energy expression, and if the field is positive, that means it's shown as up, then a spin in the +1 state will have energy -h, and a spin in the -1 state, that means when it is down, it will have an energy of +h. So what it means is that when the spin is parallel to the field, so parallel to the magnetic field is the lower energy configuration, because that is -h, and if it is anti-parallel, this is +h, so that is higher energy configuration. So that's one thing that has to be kept in mind. The total magnetization for a given configuration is mu, that is the magnetic moment of each one of them, multiplied by n plus and n minus. So n plus is the number of spins. If there are n, total is n plus of them are in the up state, that is parallel to the field, and n minus in the down state. So it is the n plus minus n minus multiplied by mu that gives the total magnetization, which can also be written as mu times. So this n plus minus n minus is nothing but this Sj. Sj is the spin of the jth atom or jth ion summed over all j. So we will write this quantity here as capital M equal to summation Sj over all j, because we are taking mu equal to 1 for convenience. So in the absence of any interaction among the spins, only their interaction with the magnetic field contributes to the total energy. So it is this expression which is now generalized to n number of spins, and it is just additive. So it is -h times the spin of each one of them summed over j. So that is the total energy. Now, since each spin has two states, a system of n spins will have 2 to the power n states. So let me take as an example, 3-spin system, n equal to 3. So then one has 2 to the power 3, that means 8 states, and only one of them is depicted here. So up, down, up. Suppose that is the configuration. Total is 3. That is what I have taken, out of which n plus is 2. So 2 spins, this one and this one, they are up, and 1 is down. So this central one is down. So total, as I said, is 3. And the energy of this configuration is -h, as can be seen from this expression. Now, this is not the only configuration which has this energy, because there are 3 different configurations for this 3-spin system, all of which have this energy -h. So only difference is which one is down. 2 of them are up, 1 is down. So here, last one is down, or this one is down, or this one is down. And what matters is just how many up and how many down. So you can see here, for a given energy, I can have multiple spin configurations which have the same energy. Now, let me introduce interaction. So I'm continuing with the concept of spins. I'm now considering interacting classical Ising spins in the absence of magnetic field, only their mutual interaction. So consider 2 spins, S1 and S2, interacting with each other. The strength of this interaction is given by J, such that the interaction energy E of this pair of spins is given by this expression. Now, let us consider the four possibilities: up, up, and then down, down. That means they are parallel. So if the spins are mutually parallel, S1, S2, that product is 1, irrespective of whether they are both up or down. And so the energy of that configuration is minus J. On the other hand, if they're anti-parallel, that is either up, down, or down, up, so the spins are mutually anti-parallel, and that has energy plus J. So which one is higher energy configuration and which one is lower energy configuration? Well, that will depend on the sign of J. So if J is positive, then lower energy configuration is this one, because then the energy is minus J, and anti-parallel has energy plus J. So if J is positive, then parallel configuration is the lower energy configuration, namely it is ferromagnetic configuration. Whereas if J is negative, then of course it is the anti-parallel one which has the lower energy. So now, instead of considering just 2 spins, I can consider n number of spins. I can write down the Hamiltonian for, again, those who are not from physics department. So Hamiltonian is nothing but a prescription for getting the energies of all the 2 to the power n configurations of the n spin system. So given a configuration, from this expression, we can find out what is the corresponding energy. Now, I have 2 possible ground states or possible configuration at T equal to 0, because at 0 temperature, all that matters is the configuration that lowers the energy. So all these are mutually parallel, so that has the lowest energy, and that is a ferromagnetic ground state. Of course, it may say that what happens if all of them are down? Yes, that also has the same energy. So there is a twofold degeneracy of the ground state in this case. Corresponding to that, if this J, instead of being plus, were minus, that means it were antiferromagnetic, then antiferromagnetic ground state will look like this, where every up spin is surrounded by nearest neighbor down spins, and every down spin is surrounded by nearest neighbors which are up spins. So that is an antiferromagnetic phase, whereas this is ferromagnetic phase. So these things were understood for a long time. Question is that now, of course, I have 0 temperature. What happens as the temperature is switched on? Of course, I'm thinking like a theorist, so I switch on the temperature. What happens is that we then look at a quantity which is called spontaneous magnetization. That is magnetization in the absence of external magnetic field. And that is well known to have this kind of behavior, that above certain temperature, which is called Curie temperature and denoted by Tc, this spontaneous magnetization is 0. And as it is cooled, then gradually the spontaneous magnetization keeps increasing and saturates to value 1, or its magnetization per spin. So that becomes 1. So in a ferromagnet, that is what happens. Now, this spontaneous magnetization is identified as the order parameter for this paramagnet to ferromagnet transition. Order parameter because it has a value 0 in the paramagnetic phase above Tc and has a non-zero value in the ferromagnet. So it tells us which is the ordered phase and which is not an ordered phase. So paramagnet is not an ordered phase and the ferromagnet is an ordered phase. So it distinguishes between the two with the help of this order parameter. And in the ferromagnetic phase, the magnitude of the order parameter keeps increasing with further cooling of the system. So it also gives us a measure of the amount of order in the ferromagnetic phase. So now the question is, what happens if a random fraction of the magnetic atoms and ions in a system are replaced by non-magnetic atoms or ions? Well, in principle, from theory's point of view, we'll still have an Ising model, but I'll call it a dilute Ising model, diluted by non-magnetic impurities. So it will look something like this. So these arrows that are shown here, those are still occupied by magnetic ions or atoms, but those sites where there is no spin, so those are non-magnetic impurities. So this is, remember the keywords, disordered system. So this is an example of a disordered system. However, here the disorder is in the random occupation of the lattice sites by the magnetic ions. Now, fundamental question. Does this system, a diluted system, a magnetic system diluted by non-magnetic impurities, does it still exhibit ferromagnetic order at sufficiently low temperature? Naively, one may think that well, it may still exhibit ferromagnetic order, except that now that not all of them are present, not all sites are occupied by magnetic atoms. So perhaps TC will be somewhat lower. Is this really what happens? Now, this question was addressed by many people, but this particular paper got most of the attention, published by Canella and Maidos in 1972. And what they found is that when you have low percentage of the sites occupied by magnetic ions, 2%, 1%, or about 5%, then you find, or 8%, you find that the susceptibility exhibits a cusp. And together with this, other experiments were done, neutron scattering, Mossbauer, and so on. And let me summarize the conclusion from those experiments. Conclusion was that time averaged local magnetization of individual magnetic ions is non-zero, but total spontaneous magnetization of the system is zero. What it means is that the state below the cusp temperature, this is the cusp temperature, the state below the cusp temperature is neither paramagnetic, it is not paramagnetic because the time average local magnetization of individual magnetic ions is non-zero, nor is it ferromagnetic because the total spontaneous magnetization is zero. So the question is, what is the order state and what is the corresponding order parameter? Now, before we proceed further, you see that we are using a term glass, spin glass. So what does it mean by glass? Well, if you distinguish between crystal and glass, what is the distinguishing feature is that the position of the atoms is disordered in the case of glass, but not so in the case of crystal. Same thing is happening when you look at ferromagnet and spin glass, compare and contrast them. It is here not the position, but it is the spins which are glassy. And so that's why this is called spin glass. Now, not surprisingly, adapting his theory of spin glasses to structural glasses, Parisi has made path-breaking contributions also to challenging open question in these complex systems, namely structural glasses. And there's a book also written by him and his collaborators, but I will not have time to go into this kind of glasses in this lecture. So let me come back to spin glasses. So what is so special about the alloys gold, iron, and copper manganese? Remember that when I said dilute system, I did not have iron sitting at all sites. In fact, majority of the sites were occupied by gold, which is non-magnetic, and there was just small percentage, 8%, 5%, or 2% occupied by iron. And similarly, copper is non-magnetic, and there is a small percentage of manganese dispersed there, and that is magnetic. So what is special about that? The Hamiltonian of the system can be written in this fashion, and there Jij, what is that? That is the interaction between the spins Si and Sj, and these two spins are located at the respective positions, vector Ri, vector Rj, so that this R is just the separation between these two sides. So the interaction is dependent on the separation between the two spins that we are considering. Now, it so happens that in gold, iron, copper, manganese, in this kind of systems, the interaction, this Jij is given by what is called RKKY interaction, Ruderman, Kittel, Kashuya, Yoshida interaction. And the special feature of that is that it is oscillatory and the amplitude of the oscillation decreases. That is not so important. Important point is that this is oscillatory. What it means is that depending on the distance between two spins, the interaction can be positive or negative. That means ferromagnetic or antiferromagnetic. Now, since the positions of the ions are random, the sign of the interaction between the spin pairs is also random. So what is the consequence of that? To understand the consequence, let us consider just three spins in this system. So basically, 3 iron in a gold iron, 3 iron atoms, and their separations are random. It so happens in a particular situation, suppose that the separation is such that this separation is giving us ferromagnetic interaction, whereas this one also gives ferromagnetic interaction, and this interaction here is antiferromagnetic because of the separation. Some falls somewhere here, so it is antiferromagnetic. Now there is a problem. Problem is that if I start from here and put it up, then this is ferromagnetic. This would like to be up. That's fine. But when I come to this third spin, now this is up. This is up. Since this interaction is ferromagnetic, it would like to be up to lower energy. But then if it is up, there's a problem here because this is up, and if this is also up, this is antiferromagnetic, it should have been actually down. So this spin is, it doesn't know which one to orient, up or down. Either way, there will be one of these two interactions which it cannot satisfy. So there is a frustration here. That is the concept of frustration. So thus, disorder naturally gives rise to frustration in gold, iron, and copper manganese alloys. But as I'm going to show next, that existence of disorder is not necessary for causing frustration. Here, I just briefly mention an unverified story. It is a story that has been going around for the last 40 years almost. Gerard Toulouse attended a lecture in 1976 in which Phil Anderson wrote on the blackboard, the name of the game is frustration. And we don't know, whether he actually explained this concept of frustration there, but what we know from the published record is that soon thereafter, both of them, that means Anderson and Toulouse, independently introduced the formal theory of frustration. So what is frustration? Let us discuss frustration without disorder. So if I have already explained this. So if I have, ferromagnetic interaction and one antiferromagnetic interaction here, this spin doesn't know which way to orient. So there's a frustration. Now, if I have a square placket here, so I have ferromagnetic, but this one is antiferromagnetic. Again, there'll be one spin, which is, either way, it is going to satisfy one link, but cannot satisfy the other. So I can define a frustration function. The frustration function is written as phi, and it is a product of the sign of the J, that is sign of the interaction going around the placket. What is common between these two, as you can see here, that if I go around this entire placket, this product will give me -1, and here also it will give me -1. So a placket is frustrated if this frustration function has the value -1. If it is +1, then all the bonds can be satisfied. So this concept of frustration was actually defined in a certainly different way and in a more general fashion in this paper by Anderson, but I'll not get into the details of that. So let me summarize. Spin glass is something that has disorder and frustration. Now, capturing these two, let us make a model, and this is a theorist model of a spin glass. Spins are present on all the sides of a lattice, so site occupation by the spins is non-random, but the interaction Jij between the spins labeled by the indices I and j is a random variable chosen either from a Gaussian distribution with zero mean. That's one choice. The other choice is allowing the interactions to be +j or -j with equal probability. Both these have been used extensively in the literature. So to my knowledge, the first theoretical paper on this was written by Sam Edwards and Phil Anderson in 1975 in this paper. And this is the title of the paper. And so what they pointed out is that there is a close similarity of this problem with that of something in polymer science. So without going into the detail, the point they made is that if you look at a particular spin at a time t, and again you look at later time t plus tau, that means there's a time separation of tau, then and if this symbol is used for time averaging, then this spin has some kind of a memory. It is sort of a frozen in a given direction. And it is this freezing in time that makes it different from paramagnets. And this order parameter that they introduced is called, of course, obvious reason, Edwards-Anderson order parameter. And what they said is that the structure is similar to standard Curie-Weiss theory with the proviso that as t goes to 0, q goes to +1 and not -1, etc. Actually, that is not true. This is not the correct order parameter to use for describing these phase transition. So that was just the beginning of my story. So soon after that, this classic paper was written by Sherrington and Kirkpatrick. And what they did, we means the authors, consider an Ising model in which the spins are coupled by infinite range random interaction independently distributed with a Gaussian probability density. Now, why did they consider infinite range interaction? Again, they explain it. It is well known that molecular field theory, that is mean field theory, which Edwards and Anderson had used. Now, of course, mean field theory is something much older, and it is well known for pure ferromagnet. This molecular field theory becomes exact when you have infinite range interaction. And so motivated by that, they solved the infinite ranged problem also here. So namely, they consider the interaction range to be infinite. And doing that, what did they find? Of course, I'm coming to that. But before that, let me explain the subtleties that were there. What one has to look at is a concept of quenched disorder. Now, quenched disorder involves two distinct averaging processes. So consider a spin system whose Hamiltonian is given by this, which depends on the spin configuration, but also on the spin-spin interactions J, and that's why I have put a subscript here, J, where the random numerical values of the latter means J, are distributed according to the probability distribution Pj. And then what one has to do is the following. For given J, one has to first calculate the free energy per spin by the standard method of equilibrium statistical mechanics. This is called partition function. And then one has to do an averaging. Now, there is one concept here. What is meant by quenched? Now, suppose the J, that is the exchange interactions between the spins in the given sample of the material, are not known. And that is the realistic situation. They are not known to us directly, but the probability distribution of the J's is known. The changes in the J's, if any, happen on time scale that are many, many orders of magnitude longer than those on which the faster changes of the spins occur. That's, for all practical purposes, the J's are frozen in time, and that's why they're called quenched. Such randomness or disorder is called quenched disorder. And the consequence of this is that when we calculate the free energy per spin, first we calculate the free energy for a given spin configuration, and then we average over the spin, for a given exchange interaction configuration, and then we average over the distribution of the interactions J. So this is the prescription for calculation. Now, why do we need a trick? So let me explain that trick. The trick is called replica trick, which is older than spin glass concepts. So replica trick enables computation of the average of free energy. That is something that we have to do from the average of the partition function using just this relation. So relation is that we have to calculate this average of free energy, which essentially boils down to calculation of the log of the partition function for given J over the distributions of J. And that one can do by first calculating the average of the partition function and then taking this limit n going to 0. But what is this n? N is the uncoupled replicas of the system. Now this appears at this stage just a mathematical trick. The replicas are brought in just for doing the calculation. So before the averaging, we just have sum over Hamiltonians of the various replicas, but then averaging over the disorder leads to coupling between the replicas, and that is where further complexities arise. Now, when Sherrington and Kirkpatrick did their calculation, what they found that at 0 temperature, the entropy becomes negative, and that violates the third law of thermodynamics. So there is certainly something wrong in their calculation. But they speculated that this unphysical behavior might have its mathematical origin in the interchange of the limits, two limits. One is the number of spins going to infinity, thermodynamic limit, and the other is number of replicas going to 0 that you need for doing the replica trick. This speculation turned out to be incorrect. Then the correct hint came from this work by Thouless and his collaborator, and they found that there is an apparent instability in the Sherrington-Kirkpatrick solution. The nature of this instability suggests the symmetry between the replicas should be broken in the spin glass phase, but we have not been able to exploit this idea to calculate the properties of the spin glass phase. So the right track was pointed out here. There is an instability in the Sherrington-Kirkpatrick solution, and most probably the culprit here is the symmetry between the replicas, which was assumed by Sherrington and Kirkpatrick. So way out is that this replica symmetry has to be broken. So let me again explain. What Sherrington and Kirkpatrick did is that irrespective of which pair of replicas that you consider, the Q alpha beta, that matrix elements were all assumed to be same. Of course, the diagonal elements for obvious reason have to be 0, but all off diagonal elements were assumed to be same. So that is the replica symmetry. Irrespective of which pair you pick up, they're all equivalent, and so all of them are just Q. Now that is replica symmetry, and replica symmetry has to be broken. So Bray and Moore made the first attempt to do that, but this was only partly successful. It was really not successful. So history was made by Parisi in these three papers written between 79 and 83. It's just a side remark I'll make that, this is exactly when I was doing my PhD, started in 80 and finished in 84. And that was an exciting time because that is when Parisi, made this fundamental discovery for which he got the Nobel Prize. So what did he do? Okay, so let me point out schematically what he did. So as I said, Sherrington and Kirkpatrick assumed replica symmetry. Then Parisi step by step broke that symmetry. So what you do is that you start with all the Qs assumed to be suppose Q0, and then you break it up into blocks. And in this block, that along the diagonal, you make them Q1, not Q0, so different. And then you continue this kind of breaking. So you keep breaking. So you started with Q0, these were Q1, then you go there, retain them as Q1 again, off diagonal blocks, and the diagonal blocks make Q2, and then further break them into smaller blocks and continue this. The conceptual difficulty that most of the people had at that time is the subtlety of the replica approach, and that is due to the peculiar situation that one must take the limit n going to 0, vanishing number of replicas. You started the n number of replicas, and that is disappearing, vanishing, and you have to compute the off-diagonal elements of that 0 by 0 matrix Q alpha beta. A very, very strange kind of situation. So to understand what is meant by the symmetry and symmetry breaking, let me now sketch some ideas of symmetry breaking. First, consider a ferromagnet. In a ferromagnet, if you look at the Hamiltonian, you have this SI-SJ interaction, and this Hamiltonian remains invariant when you flip the sign of all the spins. That means SI goes to minus SI. This is what is shown schematically here, that I have minority of the spins in the down and majority are up. So magnetization is positive. If I now flip the spins, so the red ones have become up and black have become down. Now the majority are in the down state and minority in the up state. So the magnetization is negative. So what it means is that the Hamiltonian has a symmetry, namely up-down symmetry, which is called Z2 symmetry. And that symmetry is spontaneously broken at the Curie temperature. Of course, strictly speaking, this happens only as n, the number of spins goes to infinity. That is sort of easy to see. If you look at the ratio of P minus by P plus, what is P minus and P plus? These are the probabilities that the system will be in the positive and negative magnetization states. And if you find that if you apply a magnetic field, an infinitesimal magnetic field will then pick up either positive or negative magnetization state, depending on the magnetic field that you have switched on, whether it is positive or negative. Okay, so that is something that is known to the experts, but then it helps in introducing the concept of pure states. So as the external magnetic field approaches 0, depending on its sign, two different equilibrium states can be defined at 0 field. It is either positive or negative. In contrast, every spin configuration S, for every spin configuration S, there is a reverse configuration minus S. That means every spin of this configuration, if they are flipped, you get this configuration, both of which have the same energy because of the Hamiltonian, and it has that particular structure. So hence, the same Boltzmann-Gibbs weight is given to both of them, and that's why unrestricted ensemble average is 0. Whereas here, the restricted ensemble either will give you plus or this minus. What it means is that this unrestricted ensemble average is basically a mixture of these two. So use of the limit h going to 0 from positive side or negative side essentially means that we are doing a restricted ensemble averaging. Now, finding the field that needs to be applied for evaluating average over a restricted ensemble was easy in the case of ferromagnet because we knew the symmetry operation Z2 that connects the two pure states. Similar approach was not possible in case of spin glass, and that's why it was so complicated. Well, here again, I would draw your attention to Anderson's prophetic statement in this paper in 1972. At some point, we have to stop talking about decreasing symmetry and start calling it increasing complication. So let's see what was done by Parisi in that context. So let us define overlap between two pure states. So it is sort of the similarity between the two states, alpha and beta, by this Q alpha beta. What is this Mi alpha and Mi beta? Mi alpha, for example, is the average magnetization of the ith spin in the pure state alpha, and similarly for beta. Now you define the probability distribution PQ of the overlaps between the pure states. So P of Q is given by this, where this symbol, the square bracket with subscript J, that indicates average over different samples with different values of the random interactions J. And what are these W's? W's are the weights of the respective pure states alpha and beta. So this PQ in principle can be calculated. So if it can be calculated for spin glass, should it not be possible to calculate for ferromagnet? Oh, yes, it can be. And if you do this calculation for a ferromagnet, for T greater than Tc, you find a delta function at 0, and below Tc, you find that there are two such delta functions. So Parisi, Mezza, and Virasoro in their classic book of spin glass theory and beyond write this. PQ is an order parameter function which can be used for characterizing usual phase transitions. For example, this bifurcation of delta function to 2 at critical temperature in the case of ferromagnet. But of course, the same now can be taken over and we can use it for the spin glass, and that is what was done by Parisi. Now notice that all the information on the mutual overlaps of the pure states are encoded in the form of this matrix Q, in the sense that PQ, the probability distribution of the overlaps, is the fraction of the matrix elements which take value Q. It's of course a little complicated, very unusual, but that is what it is. So still, till 84, for about 4 years, people are still not clear about the what is intuitively physically meant by this P of Q, etc. So in this paper, again, Parisi and collaborators, they pointed out that the space of states of the spin glass has an ultrametric topology. It was a new concept for physicists, although known to mathematicians, and that's why Ramal, Toulouse, and Virasoro wrote this nice article in Reviews of Modern Physics explaining the concept of ultrametricity for physicists. So what is that concept? Recall the triangular inequality in elementary Euclidean geometry. So we have a triangle and vertices 1, 2, 3. The distance 1, 3, the distance between 1 and 3, that is less than or equal to the distance between 1 and 2 and sum of distance 1 and 2 and distance 2 and 3. That is the standard thing that we learned in very elementary Euclidean geometry in middle school. Well, for a spin glass now, we can define a distance. And this is the distance between the pure states, alpha and beta, for example. And this is defined in the following way. So it is Mi alpha minus Mi beta square. So that is a D alpha beta square, where Mi alpha and Mi Si, they have the same meaning that I have mentioned earlier. Now, in this case, this is what was shown by Parisi and his collaborators. Instead of this inequality, you have a stronger triangular inequality, and that holds in ultrametric space. Namely, D13, distance between states 1 and 3, this is less than or equal to max D12, D23. That means it is the larger of the two. So this distance is less than or equal to the larger of the two. So what is this? So this is an example of this ultrametricity. A simple bifurcating ultrametric space consisting of 16 points is shown here. The distance between the points is defined by basically the number of levels one has to go up till you reach a common vertex. So distance between alpha and beta here is 1 because you go up one step and you have a common vertex. Distance between lambda and mu is also the same, 1. But distance between beta and gamma is 2. Beta is here, gamma is here. So you have to go up not one step, but 2 steps to have a common vertex. So distance between beta and epsilon, if you look at that, that is equal to 3, and so on. So this is an example of an ultrametric space. And for example, here, alpha, beta, gamma, delta could just be the different states that I was talking about in the context of the spin glass pure states. Now, again, let me graphically or intuitively try to explain this. If you look at the free energy landscape and compare ferromagnet with the spin glass, for a ferromagnet above Tc, we have just one minimum of the free energy, and that basically then at m equal to 0, spontaneous magnetic ion 0, that tells us that it is a paramagnet. And then when you go to temperatures below Tc, of course, in the absence of magnetic field, you have 2 equally deep minima So you have either positive magnetization state or negative magnetization state corresponding to the equilibrium of the system. Quite straightforward and simple. But when you come to spin glasses, what you find is that above TC, it is more or less very similar, but below TC, now you have this kind of rugged landscape where you have not just one minimum, but several minima. And that is what makes things complicated. So let me try to summarize the key features of replica symmetry breaking in the Sherrington-Kirkpatrick model of spin glass, achieved mainly by the works done by Parisi and some of these with his collaborators. First, spin glass phase consists of infinitely many pairs of thermodynamic states that are not related by any simple symmetry transformation. It's not like Z2 symmetry of ferromagnet. The description of the broken replica symmetry requires an infinite number of order parameters, in fact, an order parameter function, very unusual. The order parameters have physical meaning. These characterize the overlaps of the pairs of states. And finally, the distances between the states display an ultrametric structure. Now, Royal Swedish Academy also pointed out that Parisi has not only worked in physics, but also in many other different areas. And so let us look at a few examples of those. Parisi has made enormous contribution to optimization by taking ideas from physics, particularly the physics of spin glasses. In order to understand what is the relation between optimization problems and problems of statistical mechanics, let us first look at this slide. Consider an optimization problem defined by a set C of configurations of a problem and a cost function E defined on this set. The aim of optimization is to find a configuration C star corresponding to the lowest cost. Now introduce a positive parameter beta, it's just a parameter, and assign a Boltzmann type probability to the configurations. So exponential e to the power minus beta E of C. So this is the Boltzmann kind of probabilities that we define. Notice that this E of C, that cost function, is the analog of energy or Hamiltonian, and beta, the way I have introduced beta here, is the analog of 1 by kBT, where kB is the Boltzmann constant and T is temperature. There is no temperature in this problem. So this is an artificial parameter that we introduce. And in the limit, beta going to infinity, which is analog of zero temperature limit, the probability distribution P beta approaches a delta function at the minimum E configurations, C star. So that is the strategy. And for those of who may be interested in details, more details can look into these books. So let me take an example of an optimization problem, a very famous one, namely the traveling salesman problem. And that has been analyzed both numerically by simulated annealing and analytically by replica trick that Parisi has extensively used. So simulated annealing, what does it do? So Kirkpatrick, who remember, he was involved in the Sherrington-Kirkpatrick model, which revolutionized our understanding of spin glasses. So he was also somebody who introduced and sort of extensively used simulated annealing. So the physical properties of spin glasses at low temperature provide a possible guide for understanding the possibilities of optimizing complex systems subjected to conflicting constraints, frustrating constraints. And what is the trick? The trick is that this consists of first melting the system being optimized at a high effective temperature, then lowering the temperature by slow stages until the system freezes and no further changes occur. That means it has gone to a local minimum of the free energy. At each temperature, the simulation must proceed long enough for the system to reach a steady state. The sequence of temperatures and the number of rearrangements attempted to reach equilibrium at each temperature can be considered an annealing schedule, which material scientists are very much familiar with. They do regularly. This temperature is simply a control parameter in the same units as the cost function. And that is something that I already mentioned. So this again was sort of used getting ideas from spin glasses where this was first employed. Okay, so simulated annealing, example, the traveling salesman problem. What is that problem? Given a complete graph of endpoints and the distances dij between all pairs of points, TSP, the traveling salesman problem, is an optimization problem. One is to find a cycle of minimum total length. And this problem, of course, was tried with simulated annealing, but with analytical technique, it was, to my knowledge, first Meza, Mark Meza here, shown here, and Parisi, they applied replica trick for getting an analytical estimate of this traveling salesman problem. Next problem, graph bipartitioning problem. Again, ideas of spin. Yeah.
The time 4:50. So
yeah. So I'll take another 5 to 7 minutes.
Yeah.
Okay. So graph bipartitioning problem is again another optimization problem. There I'll not then go through all the details. This problem can be again mapped onto a spin problem. The only important thing to remember is the following. So let me see. You have basically a dilute ferromagnet. Effectively, after you map it onto a spin problem, we have a dilute ferromagnet, but then there is an antiferromagnetic constraint which brings in the ingredients of spin glass. So this competition between effective ferromagnet and antiferromagnetic interaction gives rise to frustration and hence analogy with the spin glass. So this problem was again studied by Anderson and his student Yashin Fu, and a related problem of weighted matching problem, which is related to this problem, that was studied by Meza and Parisi, again applying the replica trick. In fact, there are other problems where Meza and Parisi have applied spin glass ideas. So that is the random satisfiability problems and so on and so forth. Parisi has done a lot more things. So for example, he came out with this idea of immunological memory. And in PNAS in 1990, he published this paper, A Simple Model for the Immune Network. And this was an attempt to explain the existence of immunological memory. And he drew attention to the fact that there are similarities with the spin glass model and neural networks. So this is also a very sort of visionary paper, I would say, that he wrote on immune system. Then Parisi also wrote a path-breaking work of what is now known as Carter-Parisi-Zhang equation. So what is this work? So two-dimensional growth processes. So this was the first paper written on surface growth models by Eden, and his model was referred to as Eden model. Then after a few years, an analytical formalism was developed by, again, Sir Sam Edwards and with him Wilkinson, and this is called Edwards-Wilkinson model of surface growth. However, there are certain things that were missing in all this, and that is what was brought in by Parisi together with Carter and Zhang. So this paper is on dynamic scaling of growing interfaces. In this paper, they wrote down this equation, which now goes under the name of KPZ equation, Carter-Parisi-Zhang equation. It's an interesting equation. It's a nonlinear, stochastic, partial differential equation. And by analyzing this, of course, they got some results, which I don't have time to get into. But apparently, by doing some work on this, somebody has also got Fields Medal. So it's a very rich, this equation very rich, both in physics content as well as in mathematics. Since I don't have time, I will skip those details. Parisi has, in more recent times, worked also on swarming and flocking. So this is, to my knowledge, his first paper on this. So interaction ruling animal collective behavior depends on topological rather than metric distances, etc., etc. And in this, of course, they also analyze experimental data. So flocking is a collective phenomenon. So this is an interesting, Royal Swedish Academy says this. Parisi has also studied many other phenomena in which random processes play a decisive role in how structures are created and how they develop, and deal with the questions such as, why do we have periodically recurring ice ages? Is there a more general mathematical description of chaos and turbulence, turbulent systems? Or how do patterns arise in murmuration of thousands of starlings, these birds? This question may seem far removed from spin glass. However, Parisi has said that most of his research has dealt with how simple behaviors give rise to complex collective behaviors, and this applies to both spin glasses and starlings. Well, so this brings us to the question that we started with: what is a complex system? To my knowledge, there, of course, many papers have been written to define this, but three defining papers are these three. Warren Weaver, who was a father of machine translation, he wrote this paper in 1948 with the title Science and Complexity. And then Herbert Simon, who got Nobel Prize in Economics, and he wrote paper, The Architecture of Complexity. And finally, Philip Anderson wrote this paper, More is Different, Broken Symmetry and the Nature of Hierarchical Structure of Science. So let me just briefly mention the concept of complex systems, starting now with Herbert Simon. In this paper, Simon says that Weaver, in this paper, has distinguished two kinds of complexity, disorganized and organized. We shall be primarily concerned with organized complexity. So roughly, a complex system, of course, is made up of large number of units. They interact in a non-simple way, etc. And what he mentions is a very interesting thing, that he says complexity takes the form of hierarchy. The complex system being composed of subsystems that in turn have their own subsystems and so on. The central theme that runs through my remarks is that complexity frequently takes the form of hierarchy. And as I have argued today, that when you look at spin glasses, there is this hierarchical structure that is built into, for example, the ultrametricity. Let me now come to this paper by Anderson. And Anderson says the behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of simple extrapolation of the properties of few particles. Instead, at each level of complexity, entirely new properties appear. And he says the symmetry of is of great importance, but then we have seen replica symmetry breaking was needed to understand the spin glasses. Interestingly, he also says that at least one further phenomenon seems to be identifiable and either universal or remarkably common, namely ordering in the time dimension. And Edwards-Anderson order parameter is a measure of spins frozen in time. Now, finally, Parisi's direct contribution to climate science, because what is the connection between his work and the work of the two other Nobel laureates this year? Well, Parisi wrote this paper in the journal Tellus. By the way, Tellus means earth in Latin. And in this paper has a title, Stochastic Resonance in Climatic Change. First of all, what is stochastic resonance? Just imagine that you have this potential which has two minima. So it's bistable. And now periodically we modulate this in a way that one of them has become deeper, and then then the other one has become deeper and it's back to its original form. So this is periodic modulation. But if you have a noise there, then of course noise can also cause transition between the two. So in a beautiful way, this was explained in this paper. So it seems like magic. In an attempt to make it audible, you feed a faint signal, a wave of a particular frequency through an amplifier, a strange black box that you bought at a junkyard because your proposal to buy a proper one was turned down once again. Of course, you hear nothing. The darn thing doesn't seem to work. Out of sheer destructive frustration, you add some random noise to your signal, and voila, suddenly you hear it. The noise, rather than blurring your signal, makes it come through loud and clear. Take the noise away and the signal vanishes again. And that is actually the core of stochastic resonance. Okay. So this paper that Parisi and his collaborators wrote, of course, is based on stochastic resonance. How is it related to the other works? Well, best way I can put it is the following, that if I now quote from this paper of Hasselmann, also that appeared in this journal Tellus, Stochastic Climate Models. And there he writes, a stochastic model of climate variability is considered in which slow changes of climate are explained as the integral response to continuous random excitation by short period of weather disturbances. The coupled ocean atmosphere cryosphere land system is divided into a rapidly varying weather system, essentially the atmosphere, and a slowly responding climate system, the ocean cryosphere, vegetation, etc. So this timescale separation, random fluctuations of weather and slow variation of the climate, that indirectly was sort of incorporated in the model that Parisi developed, and that is where they showed the existence of stochastic resonance to explain the ice ages, etc. So Parisi's contribution doesn't end there. His contribution in high energy physics is enormous. In fact, just yesterday, I looked at his Google Scholar page, and if you look at his first paper, Asymptotic Freedom in Pattern Language. And then next one, of course, his book on spin glasses. Then comes his KPZ paper. Then planar diagrams, again, something in field theory, not in spin glasses. Simulated tempering is a Monte Carlo, scheme. And then, statistical field theory is his book. Okay, and if you keep going down, again, you find perturbation theory without gauge fixing, which is again in high energy physics. And then comes his climate change paper on this similar structure, fully developed turbulence. And then comes his paper, the first paper on spin glasses, where infinite number of order parameters were introduced. So sometimes people can get large number of citations for a paper, but not Nobel Prize, and far fewer citations and get a Nobel Prize for that, depending on the conceptual breakthrough. And in fact, if you go through his other awards that he has got awards also internationally, very high regard awards for his works in other areas of physics, in particle physics, quantum field theory, and so on. So it is it's very interesting to see such a versatile physicist of our time. Conclusion. Well, as far as complex system is concerned, this is taken from Wikipedia, so the definition, as you can see, is really something that allows many areas to be incorporated in the definition of a complex system. For me, I will end with this poem from D.H. Lawrence, The Third Thing. Water is H2O, hydrogen 2 parts, oxygen 1. But there is also a third thing that makes it water, and nobody knows what it is. And for complex systems, we know the components, but then there's a third thing. It is the collective behavior that emerges. That is the emergent property. So before I end, I would like to acknowledge the advices that I have got throughout my career, from my mentors, advisor, and well-wishers, my supervisor, Professor Mukherjee, Professor Majumdar at IIT Kanpur, and Professor Philip Anderson, and financial support from my JC Bose Fellowship. Thank you for your attention.